Hi there, this is Astrophysics. This is Surveying the Stars, Lesson 4, and this one is Absolute Magnitude. So we've done apparent magnitude, which is how bright a star appears to be from Earth, regardless of its distance away. So what we do with this is mathematically place all of the stars at a set distance of 10 parsecs away, and then mathematically calculate what their brightness would be at that distance. So there's the definition. The absolute magnitude m of a star is equal to its apparent magnitude if it were placed at a distance of 10 parsecs from the Earth. So the equation, m minus m equals 5 log, and it's log base 10, d over 10. So distance is in parsecs, and the log is to the base 10. Okay, so lowercase m is apparent magnitude, uppercase is absolute. And let's have a look at a couple of questions. So the first one is relatively a little bit trickier, but you should be okay. The second one is quite a step up. Right, so let's have a look at that. So here's the first one if you want to have a go at it. All right, let's have a look. So question 1, calculate the absolute magnitude of the sun if its apparent magnitude is minus 26.7. So the first thing that we need to do is to calculate the distance to the sun in parsecs. So there's a couple of ways of doing this. So on the data sheet, you've got the distance to the sun, and you've also got how many meters are in a parsec. So let's do that. Distance to the sun is 1.5 times 10 to the 11 meters, divided by the number of meters in a parsec, which is 3.1 times 10 to the power of 16 meters. So that gives us distance to the sun in parsecs of 4.84 times 10 to the power of minus 6 parsecs. So what I'm going to do is put that value up here. So distance is 4.84 times 10 to the power minus 6 parsecs. Let's make some room, and then we'll finish the calculation using the equation. Right, so m minus m equals 5 times log to the base 10, distance over 10. So what I suggest is that you can do it like this. You can do minus 26.7 minus m equals, then the right hand side is going to be 5 log base 10, and the distance is 4.84 times 10 to the power minus 6 divided by 10. So basically what you should do is 4.84 to the minus 6 over 10, log that value, and then times your answer by 5. So log to the base 10 of that calculation is minus 6.315, and then you need to times that value by 5. So what we end up with is minus 26.7 minus the absolute magnitude equals minus 31.576. Then you just need to rearrange to find m. So I'm going to times it all by minus 1. So that would be 26.7 plus the absolute magnitude equals 31.576. So the absolute magnitude is simply 31.576 plus, sorry, not plus, minus 26.7. So that gives an absolute magnitude that rounds to 4.9. Now you might be wondering, well, that's all well and good, but what does that actually mean? So it's the same as the apparent magnitude. So the lower the number, and as it goes negative, the brighter the star is. So stars typically go between, so a typical star could go between minus 10 for the really, really bright ones, all the way up to plus 20. So the sun's a very average star, so 4.9 makes sense. Apparent absolute magnitude is going to go much lower. So if you're looking at a galaxy, for example, so there's a giant elliptical galaxy, M87. You've probably heard of it. Well, probably not. But that's got an absolute magnitude of minus 22. And for a bit of context, if you've got 60,000 stars of absolute magnitude minus 10, that's how bright that galaxy is. So same scale as the apparent magnitude, lower the number, the brighter it is. Right, let's move on to question 2, the more challenging one. Right, so if you want to have a go at this one, if you want to pause. Right, let's have a look at it. So Sirius has an apparent magnitude of minus 1.47, and we're going to calculate the distance in astronomical units it would need to be from the Earth to equal the brightness of the Sun's apparent magnitude. So there's quite a few steps in this one. So first of all, what we need to do is calculate the absolute magnitude of Sirius. We need to know exactly how bright it is if we put it at a distance of 10 parsecs. So to do that, first of all, we need to get the distance of Sirius in parsecs. So we've got some information here. So we've got that it's 8.3 light years away. And if we divide that by the number of light years in a parsec, that will tell us how many parsecs away it is. So 2.55 parsecs is the distance to Sirius. And then what we're going to do is use our equation. So we've got m minus m equals 5 log base 10 d over 10. So the apparent magnitude, minus 1.47, minus absolute magnitude equals, on the right hand side, 5 log base 10, 2.55 divided by 10. So let's do the right hand side first. So 2.55 divided by 10 is obviously 0.255. And then if we log that, we get minus 0.59. And then we need to times that value by 5. So what we end up with is minus 1.47 minus the absolute magnitude equals minus 2.97. Times it all by minus 1. So we get 1.47 minus the absolute magnitude plus the absolute magnitude equals 2.97. So the absolute magnitude of Sirius comes out at positive 1.5. Then what we need to do is do the equation again. I'm just going to make some room. Should be enough. We're going to give it the apparent magnitude of the Sun and figure out how far away it would need to be. So m minus m, so minus 26.7 minus the absolute magnitude, so minus 1.5 equals, then we've got 5 log base 10 d over 10. So what we need to do is rearrange to find d. So I'm going to talk you through that. So you've got minus 26.7 minus 1.5. So on the left-hand side, we get minus 28.2. And then what we're going to do, first of all, is divide by 5 to get rid of that 5 on the right-hand side. So on the left-hand side, we end up with minus 5.64 equals log base 10 d over 10. So what we need to do is to get rid of the log base 10. So if you do shift log on your calculator, you get the anti-log. So what we end up with is this. So we end up with 10 to the x, so 10 to the minus 5.64 is equal to the distance that we're looking for divided by 10. So to get that distance, we need to get rid of the divide by 10, so times by 10 on the left-hand side. So 10 multiplied by 10 to the minus 5.64 will give us the distance that we're looking for in parsecs. So that distance d is 2.29 times 10 to the power minus 5 parsecs. And the question wants it in astronomical units, so what we need to do is multiply by the amount of astronomical units in a parsec, which is 207,000. So that gives us a distance in astronomical units of 4.74 AU. So that is the distance you would have to put Sirius away from the Earth for it to appear as bright as the Sun. And that's about Jupiter. So Sirius would have to be where Jupiter is, and when you looked at it, it'd be as bright as the Sun. Well, don't look at it, that would obviously be really stupid. Right, there we go. Hopefully that went all right, and thanks for watching.